Next up, we have Ian Billett talking about all the intricacies of the TSDB, and also as a nameless cloud provider is not on fire anymore, he's even able to join us afterwards for the Q&A. So another round of virtual applause, please.
Welcome to this virtual PromCon North America 2020 talk. My name is Ian Billett. I'm a software engineer at Improbable, where we build and run infrastructure for online games. And the title of this talk is TSDB WTF. This is a statement that I found myself saying when I was trying to wrap my head around what the TSDB is, what it does, and how it works. But I am pleased to tell you that the number of WTFs per minute is decreasing over time, which is a perfectly scientific measurement of understanding. This talk is about sharing with you the intuition, mental models, and coping strategies that have been helpful to me in understanding the TSDB. This talk is aimed at the less experienced members of this community. It is about getting a firm grasp of the fundamental concepts that will serve you well when working with Prometheus, and also the wider ecosystem projects like Thanos and Cortex. This is very much a I wish I'd been told this kind of talk. I'm very much a visual learner, so diagrams, animations will all feature very heavily. And coincidentally, this is actually quite a good time to give this talk because there have been some changes to the TSDB in the 2.19 release that we'll mention. So we're going to introduce the core concepts of the TSDB by stepping through the right path. The right path is the sequence of steps that happen for a given piece of data to be ingested and stored in the TSDB. We will pause and discuss concepts kind of in more detail where it makes sense to. And finally, we're going to round this talk off with a recap, like cheat sheet, to solidify the things that we have talked about. So, without further ado, let's dive straight in. Firstly, the basics. TSDB stands for Time Series Database. What is a time series? A time series is a stream of timestamp value pairs that is uniquely identified by an identifier. In Prometheus, the identifier is a label set that looks like this. A label set is just a collection of key value pairs that tell you useful metadata about the time series. And when I'm feeling particularly lazy, I kind of think of this just like a JSON blob. It's kind of close enough. So the first thing I think of when thinking about the right path is, how does Prometheus get the time series data? Let's demonstrate this. So we have our Prometheus server, and we have our target. Target is the terminology used to refer to a thing that we receive data from. Technically, it is like an IP and port combination. It is deliberately an abstract phrase, as we could easily be scraping different ports on the same VM or pod or whatever. You might ask, how does Prometheus know about the targets it should be scraping? That is the topic of service discovery, and it is vastly out of scope for this talk, but there are lots of great resources out there. So Prometheus is a pull-based system. That means that it requests the data from the target. Usually this is exposed via the /metrics HTTP endpoint. The target then responds with the metrics page. This is a text response in the metric exposition format. You can look that up. In reality, there are loads of metrics on this metrics page. This is just a tiny, tiny fraction. For example, Prometheus's own metrics page exports about 340 metrics by default. Internally to Prometheus, each target is managed by a scrape loop object that pulls this data in at regular intervals, the default for which is 15 seconds. The metrics page that the scrape loop obtained from the target is then run through the text parser. This converts the raw bytes of the metrics page response into native objects that contain the time series identifier, the label set, and the timestamp that the scrape happened, and the value of the time series at that point in time. These are called samples, each of which is one value in a time series. Now, at this point in our story of the right path, we have a regular stream of samples coming in from all the targets that our Prometheus instance is scraping. The next natural question to ask is, how should we go about storing these samples? We can start to answer this question when we think about the pattern of data ingestion and the types of queries that people will ask of the data. Let's give an example of what we mean. We have our time series here on the y-axis and time on the x-axis, and as time progresses, we ingest data like so. Sometimes scrapes are missing, sometimes the targets are not scraped perfectly at each interval. This is normal and expected. But what we do see is a vertical pattern of writes. This basically means that we ingest samples from our targets all at once. However, the general pattern of a user requesting data from the system will be horizontal in nature, which means that they will likely request data for a subset of metrics over a period of time. These are called horizontal reads. Satisfying these two constraints is the core problem that the TSDB has to solve. Data is ingested in vertical slices, but it needs to be stored in such a way that supports the horizontal reads done by users. So how does Prometheus tackle this problem? Well, in part, it solves it by introducing the concept of chunks. What is a chunk? A chunk is a per time series sequential series of samples. Let's step through kind of how they work. So we have our incoming stream of samples coming from our target scrape loops. These samples are written into the head chunk, which is the chunk that is currently open for appends. The samples then fill up in the chunk like so. When the chunk contains 120 samples, it is classified as being full. Well, why 120 samples per chunk? Well, when the samples are appended to the chunk, they are encoded, and 120 samples is the sweet spot for the standard encoding mechanism. The next question you may ask is, how are the samples encoded into the chunks? This is a very interesting topic that I will not go into any detail on, and I encourage you to watch these videos that go into a lot of detail. The TLDR is that the encoding mechanism is called XOR encoding. This harnesses the regularity of scraping timestamps and linearly increasing values to compress each sample from 16 bytes down to 1.3 bytes on average. It is very impressive. When our head chunk is full, the chunk is closed to writes and a new head chunk is created to accept the incoming stream of samples. So Prometheus version 2.19 introduced the memory mapping of chunks in the chunks_head directory in the TSDB data directory. We won't go into detail, but suffice to say that this is an optimization to reduce the memory overhead of holding chunks in memory. At this point, we are happily ingesting samples from our scrape loops, and we are creating 120 sample chunks. Everything seems to be going smoothly. One problem is that we are holding all of these samples in memory. If the process crashes, we stand to lose the data that we have ingested from our targets. And Prometheus protects us against this eventuality with something called the WAL. What is the WAL? The write-ahead log is an on-disk log of every record that has been ingested by Prometheus. A record here is either a sample, a new series that Prometheus has seen, or a tombstone. And we'll explain these later on. The idea of a WAL is that every single incoming record to this TSDB is written to disk before being appended to the relevant chunk. This protects Prometheus against data loss by providing a mechanism for replaying the data into memory that was lost when the process crashed, and it's fairly common in databases. Let's see this in action. So we have an instance of Prometheus that starts up and begins ingesting samples. At some point, the process crashes, wiping all of the chunks from memory. When the process is restarted, the first thing that happens is the data in the WAL is replayed back into memory to get us back to where we were. By default, the WAL retains the last 2 hours worth of data. We will explain 2 hours very shortly. In the TSDB data directory, the WAL looks like this. And you may ask, what are these files? These are WAL segment files. So The totality of the WAL data is split between these 128 megabyte files. What is the WAL checkpoint? This is an optimization made to speed up the WAL replay process, and the WAL checkpoint contains compacted WAL segment files. Heavy load servers can have really big WALs that can take hours to reload when the TSDB is reopened, so lots of optimizations have been made. So at this point, we have a stream of samples ingested by our target scrape loops. These samples have been encoded into per time series chunks in memory, and Prometheus is protected against data loss by the WAL. The next thing we want to do is write our in-memory chunks to disk. To explain this, we must introduce the concept of a block. What is a block? A block is like a mini database. It contains your chunk data and all of the other things you need to query that data. And there are two key processes that govern the life cycle of a block. These are compaction and truncation. Let's now see how blocks work. Similar to chunks, the head block is the in-memory data structure that represents the block that is currently being filled up with data. It has some extra bits of information that we'll talk about in just a second. As samples are being ingested and chunks are being created, those chunks fill up in the head block, like so. When the head block contains 2 hours worth of data, it then becomes compactable, which basically means that it is ready to be written to disk. 2 hours is the default block value, which can be configured, and this is why the WAL retains 2 hours worth of data. Compaction is a process that takes any number of blocks as input and compacts these into a new block containing all of the information of the input blocks. Here, we are talking about it in the context of compacting the head block, but it also applies to compacting multiple on-disk blocks into bigger blocks covering a longer time range. So when the next compaction cycle occurs, which is triggered at least every minute, the head block is written to disk, like so. Once the head block has been compacted to disk, it goes through the truncation process, which basically means flushing all of its in-memory data structures ready to start being recreated by the stream of incoming samples. So, what do the blocks look like on disk? The block format looks like this. The name is some kind of encoding of the timestamp of when the block was created. You can see the chunk files here. Be careful. Seeing 2 chunk files does not mean that there are 2 chunks in the block. These are in fact chunk segment files where many chunks are embedded in a special format. These files roll over at 512 megabytes, which is the default chunk segment file size. You will also ask, what are tombstones? Tombstones represent the way that Prometheus deletes data. If you call the delete API endpoint and say, I want to delete time series X between these 2 timestamps, the data is not actually deleted there and then. Rather, a tombstone entry is created that basically says that the data of time series X between this time range is due to be deleted. When the block that contains that piece of data is next compacted, the compaction process will not include the time series data range referenced by the tombstones when the next block of data is created. So the final thing I wanted to talk about in a little bit of detail is the index. So how does the block index work? Each block contains an index. This is the thing that you use when you're trying to figure out where the chunks of data are for a time series that you care about. For on-disk blocks, this is contained in the index file, but the head block keeps these data structures in memory. So Prometheus uses an inverted index to retrieve chunk data when queried. And the key data structure here is the postings table. So a normal index would map a reference to the data, but an inverted index maps data to references. And this is very common in document-like databases. Seeing this in action will help it make more sense. Let's take, for example, a PromQL query. PromQL is the language used to query data in Prometheus. Last PromCon, I gave a talk called PromQL for Mere Mortals, so shameless plug to go check that out. When we query Prometheus, we say, hey, please return to me all of the series in the TSDB that match my query. And the query we're looking at here consists of two labels. And we are saying, please return to me all of the time series that contain these two labels. So what the postings table does is maintain a mapping of labels to time series references that contain this label. Now we know which time series have each label set. How do we know which time series have both of these labels set? And that is as simple as taking the intersection of these references. Simple. We then use these time series references to fetch the chunks to satisfy our original query. If you dig a bit deeper into the index documentation, you will find references to things like the postings offset table and the symbol table. These are data structures that are used to minimize the amount of data that we store on disk, but they don't change the rough flow that we've just explained. This concludes all of the concepts that I want to talk about today. So let's quickly recap the key things that we have discovered when stepping through the right path. A sample is the raw data point that we get from the target scrape loops. They are one entry in a time series and comprise a label set, a timestamp, and a value. A chunk is an encoded sequential series of samples. The head chunk is the chunk that is currently being filled up with samples. The WAL is a 2-hour persistent on-disk record of samples, series, and tombstones. Prometheus uses the WAL to protect itself against data loss in the case that the process crashes. A block is like a mini database that contains the chunks of samples and the data structures needed to query that data. A block lifecycles are managed by the compaction and truncation steps. Finally, an index is a per block object that tells us which chunks contain the data we care about. That's all, folks. Thank you very much for watching. I hope that your TSDB WTFs per minute now decrease over time, and I hope that you now have a more intuitive understanding for what the TSDB is, what it does, and how it works. Do reach out if you have any feedback, and I hope to see you all at the next PromCon. See ya.
So,
hello, can you hear me?
yes.
Hi, how you doing, Richie?
Fine, you?
Yeah, good. Glad that that's over.
I'm not on fire anymore.
Well, I meant the talk because it's somehow I still get the same nerves like watching a talk back than I do get it doing a talk live, but hey ho.
Yeah, I find it's a lot more horrible to talk into a computer instead of having an audience to work with. So
cool.
Yeah, sorry, I think Julian was doing Q&A. Sorry, I'll just mute myself again.
So how do we do this?
Well, reading it out, I saw a question earlier, but that was already deleted, I think, or maybe it wasn't.
I think, yeah, so there were some questions, some really good questions from Darshanime, I think that's pronounced, in the chat that I answered kind of midway through, but I guess it's worth just repeating for people that may be listening on the recording. So the first question was, does the chunk store samples from all targets, or are there chunks per target? If the former, don't we lose some XOR compressibility? So the answer there is that chunks are per time series. So one target presents its metrics page to you. In the metrics page are lots of individual time series, and it's those individual time series per target that are stored per chunk. So you do get this kind of amazing level of compressibility that Fabian and Bjorn and others kind of implemented over the time. Then there was a follow-up question to which was, are wals f-synced on every write? If yes, isn't that slow? If not, how do we not lose data in the event of a crash? So I wasn't actually quite sure the answer to this question, but Brian has very kindly chipped in. and it's not f-synced. So I'll just read out his answer verbatim. Like many other databases, it's not f-synced. That would be far too slow. The thinking is that if you lose some data, it's the same as if the Prometheus had died a few seconds before, so not like a massive problem semantically for the in the case that Prometheus crashes and you lose a bunch of data. There was another question in the Zoom chat from.
Actually, I believe one correction on that is we actually do f-sync the wall every 10 seconds.
Oh, there you go. Excellent. Thank you, Ben, very much. So there's another question from Arthur Silva-Sens in the Zoom chat, which says, from what I remember, Prometheus v1 used to create a new file at the file system for each time series ingested. This would cause a problem of opening too many files when working with a large amount of metrics. This problem was solved in Prometheus v2. How does the WAL write samples to the file system without causing this problem again? That's a really good question. So Arthur, that you're touching on a topic which if I were to do this talk again, I would definitely mention, and that is of series churn. So when you have a highly dynamic compute environment like a Kubernetes cluster where you get a new set of time series every time you roll out, or every time your pods are recreated, you get unique sets of time series because the pods have different names, etc., etc. This means that although you may have, say, 1 million active targets that you're scraping from, your the TSDB actually represents 10 times that. There have been 10 roll. So that is the
Okay, I see Julian moving, so it's Ein who just cut out.
Oh, sorry, it's probably my internet. Rubbish.
Yeah, probably if you could enable your video.
Yes. Yeah. Okay, cool. We'll try this. Yeah, so that's kind of the top concept of churn, and that kind of in like some of the larger Prometheus servers that caused Prometheus to run out of inodes on the underlying machine. So the way that Prometheus deals with this in the V2 of the TSDB, I believe, although I would happily defer to more experienced members of the community here, is that it compacts, it writes the chunks in these chunk segment files. So when you look at your TSD directory, you look in a chunk directory, you see a chunks subdirectory. There are kind of sequentially numbered chunks that I believe roll over at about 112 megabytes. And so all of these series are kind of compacted into these kind of highly optimized on-disk formats. So that's how they solve it, the inode problem in Prometheus v2. Okay, answer question. If I want to continue decreasing my TSDB WTFs per minute further, where do I start in the code? That is a funny but troll question. I think that actually touches on quite an interesting point that I'll just make here, is that kind of for someone coming to this, the code is, like the code is the implementation, but for new people, it can be quite difficult. And it was quite difficult, I'd say that openly, kind of getting my head around what's going on, what's happening, what does this mean, what does that mean? But and there's an open ticket in the Prometheus backlog to kind of talk about different sets of documentation or something that we can do to do this. So I'm going to raise a PR there and we can kind of start discussion from there. Okay, next question we have that's open. Any ideas for TSDB-next for Prometheus v3? Do we already have a number of issues with the current format? Do we need major updates for it? From Alexei Shiroki. That's a very, very good question. And that is a question that I am not best placed to answer. I believe Ganesh is doing a talk, I believe tomorrow, called TSDB A Year in Review. And Ganesh is kind of one of the main developers of the TSDB at the moment. So I would highly encourage you all to tune into that and direct those kind of questions to Ganesh. All right. We have no open questions?
No,
I still have one question.
Hi.
If I
Please.
still have 30 seconds, yes. The latest release of Prometheus enabled the wall compression by default. Does it mean that also some part in memory is also compressed, or only the wall in the disk?
The question there was that the TSDB compression has been enabled by default. Is that just on disk? I believe that is just
Okay.
on disk. Although, I mean, I would happily be corrected by Brian or Ben or Richie.
Yeah, you're correct. The WAL compression only affects the WAL on disk. The cost is it costs a tiny amount of CPU that normally doesn't matter.
Thank you.
I think that's probably it for all questions. Yeah, thank you all for listening. I hope that was helpful. And yeah, see you all when I see you, hopefully at the next PromCon.